In this video, we will discuss the F distribution and the characteristics of F distribution. The F distribution was named in honor of Sir Ronald Fisher, one of the founders of modern-day statistics. The test statistics for several situations follows the F probability distribution. It is used to test whether two samples are from population having equal variances. And it is also applied when we want to compare several population means simultaneously. The simultaneous comparison of several population means is called analysis of variance, or ANOVA. In both of these situations, the population must follow a normal distribution, and the data must be at least interval scale. So what are the characteristics of F distribution? First, there is a family of F distribution. A particular member of the family is determined by two parameters, the degrees of freedom in the numerator and the degrees of freedom in the denominator. The shape of the distribution is illustrated by the graph. There is one F distribution for the combination of 29 degrees of freedom in the numerator and 28 degrees of freedom in the denominator. There is another distribution, F distribution, with 19 degrees of freedom in the numerator and 6 degrees of freedom in the denominator. Another distribution with 6 degrees of freedom in the numerator and 6 degrees of freedom in the denominator. As you can observe, the shapes of the distribution changes as the degrees of freedom changes. The second characteristic, the F distribution is continuous, meaning the value of F can assume an infinite number of values between 0 and positive infinity. Third, the F statistics cannot be negative. The smallest value of F is 0. The F distribution is positively skewed. The long tail of the distribution is to the right-hand side as the number of degrees of freedom increases in both the numerator and the denominator. The distribution approaches a normal distribution. The F distribution is asymptotic, meaning as the values of F increases, the distribution approaches the horizontal axis but never touches it. This is similar to the behavior of normal probability distribution. So how do we test for equal variances? For a two-tailed test, the test statistics is given by the formula. F is equals to S sub 1 squared over S sub 2 squared. The degrees of freedoms are n sub 1 minus 1 for the numerator and n sub 2 minus 2 for the denominator. S sub 1 squared and S sub 2 squared are the sample variances for the two samples. The larger S is placed in the denominator. The null hypothesis is rejected if the computed value of the test statistics is greater than the critical value. Let us have some example. Colin, a stockbroker at Critical Securities, reported that the mean rate of return on a sample of 10 internet stocks was 12.6% with standard deviation of 3.9%. The mean rate of return on a sample of 8 utility stocks was 10.9% with standard deviation of 3.5%. At 0.05 significance level, can Colin conclude that there is more variation in the software stock? Before we can solve the problem, let me show you how to find a critical value using Microsoft Excel and using distribution table. So in this problem, as we can see, the n sub 1 or the first sample is equals to 10. So n sub 1 is equals to 10 and n sub 2 is equals to 8. So n sub 1 again is equals to 10 and n sub 2 is equals to 8. So to use Microsoft Excel, first, let us, you click formula and then you go to statistical and then you find F inverse right tailed. So you click F inverse right tailed. Okay. So in the problem, the level of significance is 0.05. So you input 0.05 And then the degrees of freedom for 1 is 10 minus 1 is 9. And the degrees of freedom for 2 is 8 minus 1 is 7. So you click OK, and then you can see the critical value for degrees of freedom, df equals to 9 and df equals to 7 is equals to 3.67. If we rounded it, we will have 3.68. So our critical value is 3.68. So that is how we find a critical value using Microsoft Excel. The second method is using the distribution table. So here is an example of a distribution table with 0.10 degrees of freedom or 10 degrees of freedom, 10%. And then we have 0.5 or 0.05 degrees of freedom. So we can use this table. So again, our degrees of freedom is 10 minus 1, which is 9 for the numerator. Degrees of freedom 1 here. And then degrees of freedom 2 is here. So we have 9 and 7. We have 3.67, or that is 3.68. So that is how we use a distribution table in finding the critical value for F. So let us now solve the problem. Again, Colin, a stockbroker of critical securities, reported that the mean rate of return on a sample of 10 internet stocks was 12.6%, with a standard deviation of 3.9%. The mean rate of return on a sample of 8 utility stocks was 10.9%, with a standard deviation of 3.5%. At 0.05 significance level, can Colin conclude that there is more variation in software stocks? So in this problem, we are trying to compare the variance of the stocks. So to solve, first, let us state the null. Step 1, state the null and alternative hypothesis. So our null hypothesis is variance 1 is less than or equals to variance 2. With our alternative hypothesis, variance 1 is greater than variance 2. Step 2, the significance level is 0.005. It is given in the problem. Step 3, the test statistics is F distribution, since we are trying to compare the variance. And then step 4, state the decision rule. The null hypothesis is rejected if the computed F is greater than 3.68. Or if we are using p-value, the p should be less than 0.05 to reject the null hypothesis. The degrees of freedom are n sub 1 minus 1, or 9, in the numerator, and n sub 1 minus 1, or 7, in the denominator. Step 5, the value of f is computed as 3.9 squared over 3.5 squared, which is equals to 1.2416. So we will try to compare f of 1.2416 to our critical value, which is 3.68. So step 6, the null hypothesis is not rejected, meaning we accept the null hypothesis. There is insufficient evidence to show more variation in the internet stocks, or simply means there is less variation in the internet stocks. They are almost the same.